Hi, in this video we're going to look at mathematical operations on decimals. Now, some arithmetic operators don't work the same with decimals as they do with floats and integers. In particular, I want to point out that the div and mod operators behave differently. And of course, the div mod function will as well, since it just returns a tuple consisting of the div and mod results. So the div and mod operators still satisfy the usual equation, which I'm sure you never thought you'd see again, but here it is nonetheless. So this equation that relates the div and mod operators still holds with decimals. That hasn't changed, that's still there. But for integers, the div operator performs floor division. In other words, a div b is the floor of a divided by b. For decimals, however, it performs truncated division, which means that a div b is the truncation of a divided by b. Now for positive numbers that doesn't matter, but for negative numbers it does. So again, those pesky negative numbers are creating problems. So let's take a look. If we just do with regular integers 10 div 3, we get 3, and if we do decimal div decimal 3, we get decimal 3. So that still works the same way. You'll notice, by the way, that we don't have to change the operator. The div operator is basically polymorphic. It's, like many things in Python, it figures out that, hey, I'm working with decimal numbers. It's going to go and look for an implementation of this div method in the decimal class and use that if it finds it. Now, if we look at negative 10 div 3, when we're working with integers, we get negative 4, which is the floored division of negative 10 divided by 3. But for decimals, the result is negative 3 because it's the truncated division. So just something to keep in mind, it doesn't work the same way. Now, why doesn't it work the same way? What was the reason behind this? Well, it really boils down to how this integer division was defined in the decimal class. So let's take a look at how it's actually done. And we have a divided by b, let's say, and the top row is called the dividend, bottom is called the divisor. So the algorithm works this way. It first figures out the sign of the result, right? Is it going to be a positive result or a negative result? Then it uses the absolute values for both the divisor and the dividend. So basically it strips out any negative signs. Then it keeps subtracting b from a as long as a is greater than or equal to b. Once it's not, it then looks at the number of times the subtraction was performed, and it returns that with the sign that was calculated initially. So let's take a look at an example. It's actually really quite simple and very elegant in how it actually performs integer division. So if we have 10 divided by 3, well, the result is going to be positive. So we kind of put that aside, and then we strip away any negative signs. There aren't any, but we would in any case. And now we start doing this subtraction. So 10 minus 3 is 7. 7 is still greater than or equal to 3. So we do this again. 7 minus 3 is now 4. 4 is greater than or equal to 3. Now we do it again. 4 minus 3 is 1. Now 1 is less than 3, so now we stop. So we did this operation 3 times, and the sign was positive, so we return 3. Now if we have negative 10 over 3, well, the first thing we do is we look at the result. The result is negative. Now we go ahead and we strip out any negative signs. So now we're left with 10 over 3. So basically it's the same calculation we did before. We do 10 minus 3 is 7, 7 minus 3 is 4, right? 4 minus 3 is 1, we stop. Now we've done this calculation 3 times, and the result is supposed to be negative, so we return negative 3. Right? So that's how it's done. And basically it's the same as truncating the real division. Right? The truncation of 10 divided by 3 is 3, and the truncation of negative 10 divided by 3 is also negative 3. But this equation here, once more, is still satisfied. I just want to point that out. That's very important. The relationship between the div and mod operators has not changed. But of course, since the way that the div is performed for decimals, that means that the mod is going to be different depending on whether n and d are integers or n and d are decimals. So let's take a look at an example of that. And again, this really matters when we have a negative number. So let's say that n equals negative 135 and d is 4, right, for the numerator and the denominator. So minus 135 div 4 using integers is negative 34. But using decimals, it's negative 33. Now if we calculate the mod, negative 135 mod 4 is 1, but when we use decimals, it's negative 3. So very different results. But this result here is still satisfied. If we calculate it for the integer, 4 times negative 34 plus 1, that gives us negative 135, which is our original numerator. And if we do it for decimals, well, we have 4 times negative 33 plus negative 3, which is still negative 135. Now, what about other mathematical operations? Well, the decimal class actually defines a bunch of various mathematical operations, like square root, different logs, base 10, base e, or arbitrary bases, and so on. But, if you look at the functions that are defined in the math module, you won't find all of them in the decimal class. Some of them are not there. For example, the trigonometric functions aren't defined in the decimal class. Usually for finance and banking, it probably doesn't matter that much. Now, we can use the math module, right? So you can still apply functions from the math module to decimals. But keep in mind that what will happen is that it's first going to take the decimal, cast it as a float, and then perform the operation. So if you were to use the square root function, then if you were to use the square root function in the math module, it's really going to take the square root of the floating representation of that decimal number, as opposed to taking the square root that's defined in the decimal class, which will then use decimal numbers to perform that operation. Now, so you can use the math module, but you kind of lose the whole precision mechanism that was the reason for using decimals in the first place. So typically, if you're going to do math operations on decimal numbers, you're going to avoid the math module, unless you really have to, because you don't have a decimal equivalent. So let's take a look at an example of why it matters. So let's say that we set our context precision to 28. And let's take a look at x equal to 0.01. So this x is a float. And then we look at the equivalent decimal as decimal 0.01. I'm missing a closing quote there. So let's take the root using the math module. So math.square root of x. And then we'll look at a mixed version where we take the square root from the math module, but we apply it to the decimal version of x. And then finally, we'll take a look at the square root using the decimal class's square root function. And we call it this way. We have the number, the object, and then we call the square root method. So now if we print the root, which is the float version, we get this value here. As expected, it's not exact. If we use the mixed method, if we look at what happens with the mixed method, well, we get the same result, because what happened basically is that it converted the decimal 0.01 to its float equivalent, right, which is an approximation, and then took the square root. On the other hand, with the root decimal, which was using the decimal implementation of the square root, we get exactly 0.1. And of course, if we now take the numbers and multiply them with each other, we should get back our original number. Well, with the floats, we don't, right? We get something that's close to it, but not exactly the same, because, well, we were off already just on the square root itself. And the same thing here with the mixed method, because things did get converted to floats, so we have the same result. However, look at the decimal version, we get exactly 0.01 back. So it's a more precise calculation and a more precise representation. So next, we'll look at the code, and we'll do that in the next video. Thanks for watching, and I'll see you in a bit.